Hello everyone and welcome to lecture. In this lecture we'll talk about what's called the direct comparison test and the limit comparison test, which are sometimes known as integral convergence tests, which will tell us whether or not the improper integral for a given function will converge or diverge without having to evaluate the actual limit of the improper integral. So these are the following. There are two main ones that we're going to talk about in this lecture, which is the direct comparison test and the limit comparison test. And the motivation here between both of these tests, or for both of these tests, is the following. It's to determine whether a given improper integral converges or diverges without having to go through and evaluate the actual value. And the reason for this, that this is important, is because very often we get functions with exceedingly complicated antiderivatives. So for the last in the last lecture, we talked about the surface area of Gabriel's horn, which is the integral 1 over x times 2 pi times the square root of 1 plus 1 over x to the power 4. So we in the lecture, the previous lecture, we went through and we showed how to use actually what's called the direct comparison test, and we're going to formalize that in this lecture for this example, but also for any other example where you might have a direct comparison for the integral. The main idea being that for this integral, we showed that this function is always going to be strictly greater than the function 2 pi times 1 over x. And because this is a divergent improper integral, it's going to force, in some sense, this to also diverge. That's what the direct comparison test is saying. But the idea is that both of these tests in general can be used to prove or disprove, so to show whether or not a given improper integral converges or diverges by comparing a possibly very complicated function to a slightly simpler function that is easier to integrate. So we're going to start here with the direct comparison test. And this says the following. We say, let's say we have two functions. That are continuous on some interval from a to infinity. Now it's important to note that For the way that we're going to do the test is going to be for improper integrals of type 1, or improper integrals of type 1, specifically type 1i, on intervals from some number a, some value a, to infinity. But the idea is that these tests, the direct comparison test and the limit comparison test, apply for all different types of improper integrals. We can modify these tests to deal with improper integrals of any type. So that's type, that all of these tests will hold in general for both type 1, subtype 1, 2, and 3, as well as type 2 improper integrals, subtype 1, 2, and 3. They just become a little bit more wordy because you have to deal with different scenarios in each. But the idea is that both the direct comparison test and the limit comparison test will hold in both cases. So the direct comparison test, we have two continuous functions on some interval from a to infinity, and we have to assume that f of x is always positive and less than or equal to g of x. So f of x always is greater than 0, so it's positive, and it stays below the function g of x. If this is true, then we can state the following. We actually have two separate conclusions. The first conclusion of the direct comparison test is that if the improper integral from a to infinity of the function g converges, then necessarily the improper integral of f must always converge as well. And we can also state that to the contrary of this, if the improper integral from a to infinity of f of x diverges, so the integral of the lower function blows up, doesn't converge, it diverges, then the improper integral of the higher function, or the function that's above f, is the improper integral of g of x dx, also diverges. So there you have it. This is the direct comparison test. The idea of proving this, I'm just going to go through the proof for part 1 here, but the idea is that this is really all we need to really understand. First off, we have that, and we've shown that for any improper integral, or not improper integral, for any integral from a to b, one of the properties of the integral is that if the function, say f of x, is less than g of x, then necessarily the integral from a to b of f of x must also be less than or equal to the integral from a to b of g of x. So then if you have that the improper integral, or the limit of this as b goes to infinity, converges, then you have that 0 is less than or equal to the limit as b goes to infinity of the integral from a to b of f of x, and this has to be trapped between the limit as b goes to infinity of the integral from a to b of g of x. dx. And so if in case 1, where we assume the improper integral of g of x converges, and this value is equal to, this limit exists, and it's equal to some value, or some positive value that's less than infinity, because it converges. So what that does is that it traps the integral of f of x, the improper integral of f of x, to be between whatever that value is. This is saying the improper integral from a to infinity of f of x is trapped between 0 and L, two positive real numbers, which means that this improper integral has to exist. Now note, it's a very, very important note, I'll put 2 stars here, this does not mean that the improper integral of f of x is equal to the improper integral of g of x. This is something that is definitely not true. Right, so this equality is not true, which is why I'm going to put a big, big X through this right here. It's a very common mistake that many students make. They assume that these two values have to be equal, which definitely does not have to be the case. I mean, we already saw that with the surface area example for Gabriel's horn, right? The integral. So for the example from Gabriel's horn, the integral of 2 pi 1 over x dx from 1 to infinity is certainly not the same thing as the integral from 1 to infinity of 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th. These are not the same thing, but from the direct comparison test, we do have that the divergence of this integral right here implies the divergence of this integral right here, because the function 2 pi times 1 over x is always less than or equal to, well, it's always positive on this interval, and it's always less than or equal to 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th. So the idea here to apply this direct comparison test is always the following. If we're trying to show that a given integral converges, right, so a given f of x converges, then we have to show that there's a function above it, g of x, that also converges. Ideally, the chosen g of x would be a simpler function to integrate, and it has to be a simpler function to integrate in order to use this effectively. And if we're trying to say show that a function g of x, say, diverges, then we have to find an f of x that is below this g of x, whose integral also diverges. So it has to be a positive f of x below the g of x. That guarantees that the f of x's integral is going to diverge. That will force this g of x to also diverge. And this positive right here is also very important. We have to guarantee that this inequality is satisfied. So let's go through and see this for an example or two. So for the first example that we'll consider, we'll call it example 1. We'll look at does the integral from 2 to infinity of t times sine squared of t over 7t to the 4th minus 5 dt, does this converge or diverge? And one way always of sort of, in some sense, figuring out whether it converges or diverges. Now this again is not a proof, it's not directly applying the theorem, But we always want to, if you're asking whether an integral converges or diverges, you want to look at how the integral is behaving for large values of t. Just say how the integrand, or the function being integrated, is behaving. In this case, this is our function that we're looking at. We'll call it f of t. Is behaving what's called asymptotically. This is just a fancy word for large values of t. Doing this will give you some idea of whether to expect it to converge or to diverge. So this should always be your step 0, or your preliminary step when evaluating whether or not a given improper integral converges or diverges. So for large values of t, we typically denote this as t is much larger than 1. T times sine squared of t over 7 t to the 4th minus 5 is approximately equal to t times sine squared of t over 7t to the 4th minus 5, or not minus 5, sorry, just 7t to the 4th. Because for large values of t, think like t equals 10,000 or t equals 1 million, 7t to the 4th is a much larger value than negative 5. So this negative 5 here is not affecting this 7t to the 4th really much at all when t is very large. That's where the asymptotically comes in. So this expression is the same thing as sine squared of t over 7t cubed, which is always less than or equal to 1 over 7t cubed, because sine is always between 1 and negative 1, which means sine squared will always be between 0 and 1. And the function 1 over 7t to the t cubed, or 1 over 7 times 1 over t cubed, the definite integral of this function for any a from a to infinity dt converges based on our calculation for the integral of the function 1 over t to the p from a to infinity. I think we used x in the last lecture, but this is a good example of how you can use any variable for integration that you want. we know that this converges from the previous lecture. So this is why this is step 0, because it tells us exactly what we should do. It tells us that the function that we should use for our comparison function in the direct comparison test is this 1 over 7t cubed, and it also tells us that we expect our integral, our improper integral, to converge. And the whole reason here is the following. We choose f of t to be equal to our function, which is this t sine squared of t over 7t to the fourth minus 5. And we know that this, for any value of t, is always going to be greater than or equal to 0. And similarly, this is going to be less than or equal to t over 7t to the fourth minus 5t to the fourth. And the reason we choose minus 5t to the fourth is because whenever I make, so if you have any fraction, 1a over b minus, and I'll use this exact number, say like b minus 5, this can always be made smaller by making the subtraction here larger. So this is always going to be less than or equal to, say, a over b minus 6. And you can see this clearly if you sort of reduce this a little bit. You cancel out the a's, multiply b minus 6 and b minus 5 times both sides. So you get the equation b minus 6 is less than or equal to b minus 5, which is the same thing as negative 6 is less than or equal to negative 5. So the idea here is that if I replace this negative 5 with something that's larger than or smaller than negative 5, like negative 5t squared, it's going to make this smaller. Now this is only going to work for values of t for which we kind of preserve this the sign here, but you can check very quickly for values of t this becomes true. And you can actually figure out exactly when this becomes true. It'd be a good exercise. But so the idea is that past that t value, this inequality holds, and you're left with t over, and then 7 minus 5 t to the fourth is going to give you 2 t to the fourth, or 1 over 2t cubed. So for all values of t past the point of no return, you end up getting that this inequality is true, and therefore the improper integral, you can say, from 0, so the improper integral of this function, which is the function we're interested in, so it's from 2 to infinity of t sine squared of t over 7t to the fourth minus 5 will always be bounded above by the improper integral from 2 to infinity of 1 over 2 t cubed which itself is equal to the limit as b goes to infinity of it's going to be 1/2 times the antiderivative of 1 over t cubed is going to be the same thing as negative 3 plus 1, or 1 over negative 3 plus 1. So it's 1 over negative 2 times t to the negative 2 from b to 0, or b to 2. Or it's equal to 1/2 times 1/2, which is 1/4, times the limit as b goes to infinity of 1 over 2 squared minus 1 over b squared, which is just equal to 1 over 4. This limit is 1 over 4, so this is 1 over 16. So we conclude from the direct comparison theorem our improper integral converges. And not only that, we have that it's between, as the integral from 2 to infinity of t sine squared of t over 7t to the 4th minus 5. This integral is a value between 0 and 1/16. Let's look at another example and show how to use the direct comparison test to show that a given improper integral diverges. We've already seen an example of this. It's the surface area problem for the Gabriel's horn surface. So we'll look at the following function. This is the definite integral, improper integral from 3 to infinity of 4 times the cube root of t over 5t plus the square root of t. Again, does this improper integral converge or diverge? And again, we always want to start by doing step 0, just to figure out whether we think it's going to converge or diverge. This is not equivalent to doing the test, but this is just to give us an idea of whether we think that this function right here is going to lead us to a convergent or a divergent improper integral. So we look for very large values of t. So when t is very, very, very large, or much greater than 1, the function f of t, which is 4 times t to the 1/3 over 5t plus t to the 1/2, this is approximately equal to, for very, very large values of t, the function 4 t to the 1/3 over the faster growing function in the denominator. So 5t, the function 5t, grows at a much faster rate than the square root of t. Take any large, very large value of t, like t equals 1 million, and you plug it in here, 5t is going to be much larger than the square root of t. So this function, when t is very large, is approximately equal to the function 4t to the 1/3 over 5t to the 1, which is 4 over 5 times t to the 2/3. And we know that the improper integral of the function 1 over t to the 2/3 from 3 to infinity diverges. because this is an integral of the form or of a function 1 over t to the p, where p is a value less than 1. So we expect that the improper integral that we're looking at also is going to diverge, even though it's a much more complicated function than the function 1 over t to the 2/3. So the next step, which is the first step of the direct comparison test, is to find a function that's below our function, or below the function 4 cube root of t, 4t to the 1/3 over 5t plus the square root of t, or t to the 1/2. And we can do this by guaranteeing, right, that this denominator is larger. If the denominator is larger for certain values of t, then we're going to get a function that's smaller. So the way that we can do this is we can say, well, this is going to be greater than or equal to, this function right here will be greater than or equal to the function 4t to the 1/3 over 5t to the 1/2 plus t to the 1/2, which is the same, not 5t to the 1/2, 5t to the 1 plus t to the 1, or 5t, which is this right here. So it's the same thing for this part of the denominator, plus, and we're going to replace t to the 1/2 with just t, because for any suitable value of t on the interval from 3 to infinity, t is going to be a larger value than the square root of t, or t to the 1/2, which is going to make this function right here smaller than this function, because we're dividing by a larger number. This is going to be 4/6 then, t to the 1/3 over t, or 4/6 times 1 over t to the 2/3. So this function will always be less than or equal to this function. It's actually strictly less than this function. And so from the direct comparison test, the integral of the function 4/6 times 1 over t to the 2/3 will also always be less than or equal to the integral from 3 to the infinity, or to infinity, of 4t to the 1/3 over 5t plus t to the 1/2. And this is a p integral, or it's actually 4/6 times a p integral with p less than 1. So this diverges. And therefore, because this goes to positive infinity, it blows up to positive infinity, this expression, this improper integral, also diverges. By the direct comparison test. So there you have it. There's two good examples of how to use the direct comparison test. And we have one more test that we want to discuss in this lecture. The next test is called the limit comparison test. And this test says the following. It says that, just like before, let two functions be continuous. So we have f of x and g of x be continuous functions. On the interval from a to infinity. Again, I just want to point out that we're doing this limit comparison test for improper integrals of type 1 subtype 1. But the idea is that all of these tests apply regardless of the type of improper integral. We can go through and restate these tests using an improper integral of any type, which is very cool. And let's also assume that the following limit exists. The limit as x goes to infinity of the ratio of these two functions is equal to L, is equal to some value, where L is a strictly positive number between 0 and infinity. Then we can conclude, the conclusion of this test says that the following, it says the following integrals improper integrals will converge so will either both converge or both diverge. Means that convergence or divergence of one implies the convergence or divergence of another. So the integral from a to infinity of g of x dx and the integral from a to infinity of f of x dx. So necessarily this is saying to us a very similar result to the direct comparison test. But this test relies on a different, so we're looking at something different. So for this test, we're specifically looking at the limit of the ratio of the two functions as x gets larger and larger and larger and larger. I'll give you a little proof of this. So the idea here is that when x is very, very large, what this is saying is that if the limit of f of x as x goes to infinity of f of x over g of x is equal to L, and this is telling us that for very, very large values of x, f of x is approximately equal to L times g of x. Which means that for very, very large values of, say, b, let's say b is very, very large as well, the improper integral from b to infinity of f of x dx is approximately equal to the improper integral from b to infinity of L times g of x. So the idea here is that if this is true, then this is saying that the improper integral from b to infinity of f of x dx for very large values of b is approximately equal to L times the improper integral from b to infinity of g of x dx. So we expect these two things to do the same thing if L is a strictly positive real number. This is the it's not an exact proof, but it's the basic idea and motivation behind why this works. So let's look at this for the two examples that we talked about previously and see if we can also get this limit comparison test to work for those previous two examples. We'll start with example 2 and then kind of move back to example 1 and end on example 1. So for example 2, we're investigating whether or not the improper integral from 3 to infinity of 4 t to the 1/3 over 5t plus t to the 1/2 converges or diverges. And step 0 is essential here. So I'm not going to repeat step 0, but the main idea is that we show that for in step 0 before, that for larger values of t, this function is approximately equal to, when t is much larger than 1, our function f of t is approximately equal to the function 4 over 5 times 1 over t to the 2/3. And very often this is good enough to use. We can use this exact comparison function as our comparison function. So step 1 is going to be to choose the comparison function. In this case, we'll choose g of t is equal to 4/5 times 1 over t to the 2/3. And we'll look at, in step 2, the limit comparison test. We're going to look at the limit as t goes to infinity of f of t over g of t. So you remember, f of t is just this 4t to the 1/3 over 5t plus t to the 1/3 or 1/2 over 4/5 times 1 over t to the 2/3. So this is the same thing as the limit as t goes to infinity of t to the 1/3 times t to the 2/3, which is going to be, so you have 5 times 4 is 20. T to the 1/3 times t to the 2/3 is just t to the 1 over 4 times 5t plus t to the 1/2. And we could evaluate this limit. This is an indeterminate form of the form infinity over infinity, because the limit of the numerator is infinity and the limit of the denominator is also infinity. So this, from L'Hopital's rule, is the same thing as the limit as t goes to infinity of the derivative of the numerator, which is 20, over the derivative of the denominator, which is going to be 20 plus, and the derivative of the function t to the 1/2 is going to be 1/2 t to the negative 1/2. So it'll be 1/2 times 4 is 2 t to the negative 1/2. And the limit as t goes to infinity of t to the negative 1/2 is equal to 0. So this limit is going to be 20 over 20, which is just equal to 1. And because 1 is a real number that's less than infinity and also greater than 0, we can conclude by the limit comparison test that the following is going to be true. The function, the integral that we started with, which is the integral of 4t to the 1/2 or 1/3 over 5t plus t to the 1/2 from 3 to infinity behaves in the same way, the exact same way as the integral of the comparison function, or the integral from 3 to infinity of 4/5 times 1 over t to the 2/3. And because this function diverges, or this improper integral diverges, because it's a p integral with p less than 1, we know that this, by the limit comparison test, also diverges. And there you have it. It's a second way of proving that that function diverges by comparing it to a simple function, only this way of proving it uses the limit comparison test. For the other example, we have to, in some sense, compare both. And this kind of uses, in some sense, a combination of the limit comparison theorem along with a sort of direct comparison theorem. Because the idea here is that finding a comparison function is not always the easiest thing to do. So for the second example, example 1, for the first example, we're looking at investigating the integral from 2 to infinity of t sine squared of t over 7t to the 4th minus 5. So what we're going to do is we're going to, instead of considering this improper integral right here, we know that the sine function is always bounded, so no matter what, by a direct comparison, this will always be less than or equal to the improper integral of 7t over 7t to the 4th minus 5. So by the direct comparison test, if this thing converges, then this thing will also converge. And then we can use the limit comparison test to show that this thing does in fact converge by looking at the following. We look at, so from step 0, for this problem we showed that for large values of t, and t is very large, t over 7t to the 4th minus 5 is approximately equal to 1 over 7 times 1 over t cubed. So you're noticing that the zero step, step 0, is very important in kind of targeting and figuring out whether or not an improper integral is going to converge or diverge. But you still have to go through and do the actual test to actually finalize whether it converges or diverges. So we'll choose this function for our comparison function, our g of t. And go through and do the actual limit comparison test in step 2. So we're going to look at the limit as t goes to infinity of t over 7t to the 4th minus 5 over the comparison function, which is going to be 1 over 7 times 1 over t cubed. This limit is the same thing as the limit as t goes to infinity of 7t to the 4th over 7t to the 4th minus 5. And we can evaluate this limit. This is another indeterminate form. It's infinity over infinity. by using L'Hopital's rule. So this limit as t goes to infinity is going to be the same thing as 7 times 4, so 28 t cubed over the derivative. The 28t cubed is the derivative of the numerator divided by the derivative of the denominator, which is again going to be 28 t cubed. So these two things cancel one another, and we get that this limit is equal to 1. And because 1 is a value between 0 and positive infinity, it's a real number that's less than infinity but greater than 0, we conclude by the limit comparison test that the improper integral of t over 7t to the 4th minus 5 from 2 to infinity behaves in the same way as the improper integral of the comparison function, or the improper integral from 2 to infinity of 1/7 times 1 over t cubed. And this converges because it's a p integral with p greater than 1. So because this converges, that means that this converges, which by a direct comparison means that this integral right here, the improper integral that we started with, also converges. This is a good couple of examples to show you how to use the limit comparison test and the direct comparison test. But thank you very much for tuning into lecture today. I hope you learned something, and I hope you had a great day.